So in this video we are going to discuss the questions which appeared in CSIR JEST examination that occurred in 2021. Okay, so the first question is the volume and temperature of a spherical cavity which is filled with black body radiation R. Okay, so we are given the volume. Let's call this as V1, that is equal to V, and the corresponding temperature of the cavity is 300 Kelvin. Okay, if it expands adiabatically to a volume 2b, okay, so the volume after the expansion, that is 2b, so its temperature will be closest to, so we have to find the corresponding temperature after its expansion. So if you recall what you might have learned in the classes, so for the adiabatic expansion of the cavity, it's basically reversible adiabatic expansion, not only the adiabatic expansion but reversible adiabatic expansion of the cavity. Volume and temperature are related as B T cube, that is equal to constant. Okay, so here we can apply the relationship B1 T1 cube, that is equal to V2 T2 cube. Okay, so from here we have to determine what is the corresponding value of T2. So T2, that is equal to V1 upon V2, and then T1, okay, so this T1 and its power 1 by 3. Okay, so after substituting a value of the parameters that are given to us, T2, it comes out to be equal to 1 by 2. So because B1 divided by B2, that will give us a factor of 1 by 2, and its power 1 by 3, and multiply with the temperature T1, which is 300 Kelvin. Okay, so after solving it, we obtain that this temperature is equal to 240 Kelvin. Okay, so therefore option D is the correct one here. Let's come to the next question. The ratio Cp by Cb of the specific heats at constant pressure and constant volume for a monatomic gas in 2 dimension. Okay, so we are given a situation where we are talking about monatomic gas, atomic gas, and it is confined in 2 dimension. Okay, so the translational degrees of freedom for the monatomic gas confined in 2 dimensions, so we need only two coordinates for the description of the motion of the particle in 2 dimension. So x, let's call these as x and y. Okay, so the translation degrees of freedom for a gas of whose particles are moving freely, for one single particle, these are 2 translation degrees of freedom. Okay, and because it's a single particle, so its energy expression, it is px square plus py square divided by 2m. That's some energy of a particle which is moving freely. So that's how we are connecting the energy expression with the degree of freedom. So basically each square energy term, it represents a degree of freedom here. So the average energy per particle whose motion is in 2 dimensions, so it is equal to 2 the degrees of freedom multiplied by average contribution which is coming from the each degree of freedom, so that is equal to kBT. Okay, in 2 dimension. Okay, so for a system of total n particle, okay, so u, n particle, or the Avogadro number of particles, so u will be Avogadro number multiplied by average energy per particle, and that is equal to NA kBT, that is equal to RT. Okay, so this is per mole. Okay, this is the energy per mole of such kind of gas molecule. So from here we can calculate the Cv per mole, that is equal to du by dt. Okay, and that is equal to R. Okay, so you differentiate it with respect to t, so we obtain R only. Okay, so let me call this equation 1 and this as equation 2. So now by making use of the Mears relationship, that is Cp, that is equal to Cv plus R, because we are taking 1 mole of a substance, so Cv is how much? It is R. We have evaluated it, so R plus R, that is equal to 2R. Okay, so therefore the ratio, that is Cp upon Cb, that is equal to 2R divided by R, that is equal to 2. Okay, so therefore option B is the correct one here. So let's continue with the next problem. So the statement is the dispersion relation of a gas of non-interacting boson in d dimension is given as, okay, so we are given a relationship, dispersion relationship mean a relation between the energy and the wave vector k. Okay, so E, which is a function of k, and this is equal to a k power s, where a and s are positive constant. Okay, a and s are positive constants. Okay, so Bose-Einstein condensation will occur for all values of, okay, so we have to find the appropriate relationship between d and s such that the Bose-Einstein condensation take place. So before we try to discuss the solution for this problem, so let me just summarize some of the important the conclusion related to the Bose-Einstein condensation in 1 dimension, 2 dimension and 3 dimension related to massive boson and massless boson. Okay, so I'm going to make a table here just for the sake of clarification among the students. So here dimensions, and then massive boson, massive bosons. Okay, so where the dispersion relationship is given as E, that is equal to p square by 2m. So dimension, if you just talk about 1 dimension, 2 dimension, and then 3 dimension case. So in all these cases the dispersion relationship is given by the same result, p square by 2m, and here in 3 dimension also this is p square by 2m. The only difference is that in 3 dimension we will have 3 components. For instance, p square in 3 dimension, this is equal to px square plus py square plus pz square, and in 2 dimension p square is equal to px square plus py square, and whereas in 1 dimension p square is equal to px square. So it's only motion along 1 dimension. Okay, so now if you just although we can prove this point mathematically also, but here we need not to go through that entire mathematics. That's a a complex process basically. So here so I'm summarizing whether the Bose-Einstein condensation it occurs for the massive boson or not. Okay, massive boson mean it's a non-relativistic particle, non-relativistic particle. Okay, and here I will write results for in the next last column. It's massless boson. Okay, so massless mean it's a photon basically, for example photon. Okay, so in 1 dimension the Bose-Einstein condensation doesn't occur for massive boson. Also in 2 dimension it doesn't occur, and it takes place in 3 dimension. Yes, that's true. Whereas for the massless boson, yes, it's possible in 3D and it's also possible in 2D, but it's not possible in 1D. Okay, so therefore in order to justify the present question, so that means we have to discuss these 3 cases here. So based upon the outcome of these 3 cases, we will decide the appropriate relationship out of these given 4 relationships. Okay, so the dispersion relationship I have already written here, so let me call this result as equation 1. So for the non-relativistic particle, the first case, it's a non-relativistic particle, that is massive boson in 3 dimension, so that means I'm talking about this case. Okay, this one. Okay, so the energy momentum relationship is E, this is equal to p square upon 2m. Okay, so that is equal to h cut square k square upon 2m. Okay, so here if we make a comparison between the equation 1 and equation 2, so here s is equal to 2, the exponent of k. Okay, so here s is equal to 2 and d is equal to 3, so this implies d is greater than s, and for this system the Bose-Einstein condensation take place. Okay, similarly in relativistic case, second is in relativistic case in 3D, okay, E is equal to the energy momentum relationship. E is equal to Pc, or that is equal to h cut c k. So here, if you make a comparison between equation 1 and equation 3, okay, so compare 1 and 3. So 1 and 3 implies that s is equal to here 1, the power of k vector, okay, and a here, that's equal to h cut c in this case, okay. So and d is equal to 3. So this also implies that d is greater than s, okay. And in third case, for 2D relativistics, now we are talking about this case where the BEC Bose-Einstein condensation is feasible, okay, in 2D, but now relativistic case, okay. So E is equal to Pc, where P is given by this relationship now, okay. It's a two-dimensional case, okay. So that is equal to h cut c k. So here, therefore, s is equal to 1. S, that's the exponent of k. So here exponent of k is how much? It's 1, and dimension are, that's equal to 2. So therefore, again, for this case also, d is greater than s. So therefore, the general relationship that that is applicable in all these three cases, it is that d should be larger than s, where s is the exponent, okay. So therefore, A is the correct option here. So let's continue with next problem. The statement is, a polymer made up of n monomer is in thermal equilibrium at temperature T, okay. Each monomer could be of length A or 2A, okay. The first contributes to 0 energy while the second contribute energy E. The average length in units of Na of the polymer at temperature T equal to E by kV is given by, okay. So let's write what is given to us. So when length of the monomer is, when length of monomer is A, then it corresponds to an energy value of energy is equal to 0, whereas when length of the monomer is 2A, the corresponding energy value is how much? It is E, okay. So now the probability that we will have energy E, probability of having energy E, so that is given by Gi exponential minus beta corresponding energy E divided by sum over Gi exponential minus beta Ei, basically, okay, or E, okay. So that means here, because it's because these two energy values, they are having only one unique value, so G, it's going to be unity. Now this is a general expression. Now we will obtain we can write it here Ei, okay. So just to make it a generalized result. Now for we will write the probability for having energy 0 and for having energy E, okay. So let's see how we will do that, because we need these probabilities to find the average length of the the chain, basically, okay. So let's try to find the probability of energy value E, that is equal to 0, and that is equal to G, because it's 1, so exponential minus beta and the corresponding energy value, which is 0, divided by this sum over this Gi exponential minus beta Ei. That's basically the nothing but partition function, okay, because G, it's 1 here. So here I can write exponential minus beta into 0 plus exponential minus beta into the second energy, that is E, and that is equal to 1 divided by 1 plus exponential minus beta E. So let's call this as equation 2, okay. Now same way we can write the expression for the probability of having energy E. That's when we are talking about monomer with length 2A. So that is equal to exponential minus beta into E. So this energy, okay, exponential minus beta E divided by, now in the denominator we will have the same expression, this one, that's okay. So that is 1 plus exponential minus beta E. So let me call this as equation 3. Now the average length is given as L, that is equal to the total number of monomers and then the average length. Okay, so that is equal to A into the probability of having energy E is equal to 0. Okay, so that's why we are multiplying here with A here. Okay, so that's the length of the monomer and the corresponding energy is 0, and plus the length 2A and then the corresponding energy probability corresponding to energy E, so that is 2A multiplied by PE. Okay, so after substituting the value of P0 and PE, so we obtain this is equal to N multiplied by A into 1 upon 1 plus exponential minus beta E plus 2A exponential minus beta E upon 1 plus exponential minus beta E. Okay, so this is equal to here what we can do, because we are given that T this is equal to E upon KB, or because T that is equal to E upon KB, or this implies 1 is equal to E upon KBT, or that is equal to beta E. So that means we can replace beta E with unity here in this expression. So therefore average length, so I'm taking A outside, so N A into, so if because in the denominator we are having the same expression 1 plus exponential minus beta E, so I'm taking the LCM here and then writing NA and then 1 plus exponential 1 plus 2A 1 plus 2 exponential, because beta E is 1 plus 2 exponential minus 1 divided by 1 plus e power minus 1. So this is our result. So this can be further solved. So this is 1 plus 2 e power minus 1, and after solving it, so we will obtain this is equal to NA and then into E plus 2 divided by E plus 1. Okay, so which one is the it is 2 plus E upon 1 plus E. Okay, so in terms of NA, so therefore D is the correct option here. Okay, so our answer matches with the option D. So let's continue with the next problem. The statement is the energy level of a non-degenerate quantum system are given by the expression that is En that is equal to N E0, where N can take value from 1, 2, 3 and so on. Okay, at temperature T, the free energy F can be expressed in terms of energy, the average energy EY. So we have to identify the correct relationship. Okay, so first let's try to find out the partition function, and then from there we can evaluate the average the Helmholtz free energy. And before that, in fact, we have to make the evaluation for the average energy of the system, because somehow there we have to connect the Helmholtz free energy with the average energy. So let's see how we can do that. So first of all, let's try to draw the energy level diagram for this system which is given to us. Okay, so by assigning the different value of N, so we can obtain the various energy values. So let me call this as E1, the level 1, level 2, level 3 and level 4. The E1 we obtain when N is equal to 1. Okay, so when N is equal to 1, the corresponding energy is E0. When N is equal to 2, corresponding energy is 2 E0, and then 3 E0 and then 4 E0. Okay, so therefore the partition function for this system can be written as Q, that is equal to exponential minus beta E0 plus exponential minus 2 beta E0 plus exponential minus 3 beta E0 plus so on. Okay, now this is equal to we can take the common factor outside, that is exponential minus beta E0 into 1 plus exponential minus beta E0 plus exponential minus 2 beta E0 plus so on, and that is equal to exponential minus beta E0 upon 1 minus exponential minus beta E0, that's A upon 1 minus R. okay. And this is in principle equal to, we keep the factor in the numerator in the denominator, and that this becomes exponential beta a0 minus 1. So that is our partition function, okay. So let me call this as equation 1. Okay, now the Helmholtz free energy is given as the Helmholtz free energy, Helmholtz free energy, which is F, that is equal to minus kVt ln z. So ln z is nothing but, or ln z or ln q, because we are writing it q, not z, okay. So that is equal to minus of ln, and then this the term in the denominator here in this expression, and that is equal to minus minus will become plus, so kVt ln multiply by exponential beta e0 minus 1. So that's the Helmholtz free energy, okay. Now let me call this as equation 2. Now because we have to connect the Helmholtz free energy with the average energy of the system, so now we will evaluate the average energy for the system, and that is equal to minus curly beta of ln q, so which is equal to minus curly beta of minus curly beta of ln q is what? So ln q is minus of minus ln minus ln exponential beta e0 minus 1. So that is the ln q, okay. So minus and minus will become plus here, so curly beta of logarithmic function, that is equal to, so from here we can work out the average energy, so that will be equal to 1 upon ln, sorry, no, sorry, it is not ln but exponential beta e0 minus 1, and then again differential with respect to beta exponential beta e0, and then another differential of the exponent with respect to beta, that will give us in term of e0, okay. So that is, from here what I can do is I can write from this result, what I can do is I can write that e0 upon upon the average energy, okay, and then multiply by exponential beta 0, this factor, okay. So I am taking this on this side and bringing this on the left hand side, so into exponential beta a0, that is equal to e power beta a0 minus 1, okay. So we will make this substitution for e power beta a0 minus 1 in the equation 2. So let me call this as equation 3. So equation 2 and 3 implies that f, that is equal to kVt ln this expression, so we are going to replace this exponential beta e0 minus 1 with the this expression on the left hand side, okay. So this is equal to kVt ln e0 upon e average, so I'm writing this as like this, multiply by exponential beta e0. So this is our final expression. So further we are going to simply rearrange the terms, so that is equal to kVt ln e0 upon e average, and then plus ln e beta e naught, so that will give us ln exponential beta e naught, okay. So this can be further rewritten as kVt multiply by ln e0 upon e average plus beta e naught, so plus e naught upon kVt, okay. Or this can be further rewritten, so this is ln e0, okay. So this can be further rewritten as okay. So let me introduce another page here, okay. The last expression can be further rewritten as f, that's a Helmholtz free energy, that is equal to e0, because when you multiply kb outside the expression, okay, so while multiplying this term with the terms inside, so kbt and kbt will cancel, so we will have e naught at the beginning, okay. So e naught and then minus kbt ln e average upon e naught, okay. So that's our final answer. So if you compare with the option, so option C is the correct one, okay. So here's the option C, so this is the correct choice here. So let's continue with the last problem. We are having walls of 10 different colors which are labeled as A is equal to 1 to 10. They are distributed among different colored boxes, okay. A wall can only go in a box of the same color, okay. So that means we are having 10 different colored boxes, and the balls, they are also of different colors, okay. So and each box can contain at most one ball, okay. So let NA and capital NA denote respectively the number of balls and boxes of color A. So assuming that NA is much greater than NA, and which is greater than 1, the total entropy can be best approximated by the expression. So let's try to understand how we can do this problem, okay. So we assume that N1 walls of color 1 are distributed in N1 boxes of same color, or you can say of color 1, okay. In the same way we can make a statement N2 walls of color 2, okay, are distributed in N2 boxes of color 2. So we can extend this to the N10 balls, okay, of color 10. They are distributed in N10 boxes of color 10. Now let's continue with the first case, okay. So in first case we are having N1 boxes, and out of N1 boxes we have to pick the total small n1 boxes where we can place the n1 walls there. So this can be done for the first case. The number of ways we can distribute small n1 balls among capital N1 boxes. So let me call this as W1. So that is equal to n1 factorial, and we are choosing small n1 boxes out of capital N1, and then remaining n1 minus n1 factorial, okay. So same way we can write such type of identical expression for the other boxes also. So that I'm writing it for the last one, so for the 10th case, okay. So that is equal to n10 factorial divided by small n10 factorial into capital N10 minus small n10 factorial, okay. So the total number of microstates omega total, that is equal to W1 plus W2 plus so on W10, okay. So that will be equal to summation, okay, over A, okay, and NA factorial upon NA factorial into capital NA minus small na factorial, where A can take a value from 1 to 10, okay. So that means once this omega total is known to us, then we can find out the corresponding entropy, so which is given by Boltzmann relationship S, that is equal to kV ln omega total, and that is equal to kb ln and then summation kv ln summation na factorial upon na factorial into na minus na factorial, okay. So after applying the Stirling approximation, this expression can be written as, this is equal to or what you can say, S upon KB. I'm taking KB on the left hand side, so that is equal to this quantity. Okay, so ln then summation of this, so this is basically equal to summation, okay, and then NA ln after applying the Stirling approximation. So this will be equal to NA ln NA. So ln NA factorial will be NA ln NA minus NA, okay, minus NA ln NA and minus NA minus NA ln NA minus NA. Remaining terms, they will cancel with each other, because from here when we will apply the Stirling approximation here, so we will have NA ln NA minus NA, and then from here also we will have minus NA, and then from here we will have minus NA minus NA, so that will cancel ultimately. Okay, so this matches with the option A here. Okay, so this option A, that's the correct one here.